So we're going to learn how to do how to use the equilibrium constant now. Oh, first of all, we're still calculating with this, I guess, with these two examples, but how to actually calculate them using concentrations now, not just putting in the actual formula for them, which is all you really had to do in 17, 19. 17, 19. Yeah, those up there.
Oh, look at that. Never mind. Oh yeah, that's really coming down now.
Yeah.
You can't tell the board's on. I thought it was all.
I know, it's weird. All right, anyway, calculating Kc. I don't have any notes to give you. Just going to show you how to do it with two examples. This first one's really easy. It's very much like what you saw in 17 and 19. A lot of these guys do take a while to write, all right, because there's a lot of information to give you. You'd have to give you the equation and all the concentrations. But there is something I threw into this one that's a little different than what you saw in 17 and 19 and 24 and 26.
Moles.
Well, right, exactly. And I give you the size of the container. That is one thing we have to worry about. You see, we're talking about gases here. And what do gases do when you put them into a container? Yeah, they expand, they fill up the size of the container. So if you want to get the molarity of a gas, you got to take how many moles you have and divide it by the size of the container. You see? So that is one factor you didn't have to worry about for the ones you were doing up till now. Because you know why? In 24 to 26 you did for the homework, they were given to you in molarity, the molar concentrations. Here it's giving you how many moles you have, and it's giving the size of the container. So you do have to do that. All right? So for your own good, I suppose, so you can remember it, I want you to write these underneath what you actually have to do for the actual concentrations. It tells you have 3.01 moles of N2. That means you got to take 3.01 moles and divide it by 5.00 liters. For H2, it's going to be 2.10 moles divided by 5.00 liters. And for the NH3, it's going to be 0.565 moles divided by the 5.00 liter container. Do all of those and give me the numbers for them.
I gotcha. Liz gotcha.
Hurry up, somebody get that done. What'd you get for the first one, Liz?
0.602.
0.602 molar. That's a capital M now we could use. Let's keep our units so I can show you what happens sometimes to the Kc's units at the end. What'd you get for the second one?
0.069.
0.069. Was the first one 0.0602 or was it 0.602? 0.602? All right. So 0.0.
Wait.
No, that's not
No,
right.
that's
for
not
numbers.
right.
Yeah, I was going to say, that doesn't look right.
I selected that in.
What is it there, Harrison?
It's 0.42.
0.420? All right, so 0.420 molar. And the next one? 0.113 molar. Molar being capital M. All right, everybody got that? Now, your equation is simple enough. Kc equals products over reactants raised to their coefficients. NH3 squared over N2 times H2 cubed. Got it? So I plug my numbers in. Make sure you know how to, by the way, there's no reason I'm doing this one. It's got a cube function in there. I don't know if all of you guys know how to use your calculators to do a cube function. Hopefully you do. So NH3's concentration. Remember, here's another mistake people make. Like Shania was doing, she puts the reactants over the products. Make sure you put the products over the reactants and look them up the right way. NH3's concentration is 0.113 quantity squared over the N2's concentration, which was 0.602, and H2's concentration, which was 0.420 molar cubed. All right? Do your stuff on the calculator. And by the way, very easy to screw the easy math up here. Can you? Hey, look here. Can you do this? This guy squared divided by him times him cubed? No. If you do that in a calculator, it will not come out right. You're going to have to be careful about whether you're using parentheses, order of operations, right? Your calculator won't know. So let's see if you can all do that and get the right answer. I'll do it myself just to make sure because I can see some mistakes happening here. Try that.
How do you go up 3?
That's what I was just asking you. Do you all know how to do the
Mine's not-
cube?
Oh wait, I can do this.
You go y to the x for my calculator. I don't know what yours says.
Y to the X.
You could have a caret maybe sometimes. My y to the x because that will give you the just with third in.
Why do they
I
call
got-
them carrots?
I don't know.
286. That's what I got.
0.286, that's what I got too.
Same here.
Is it n to the negative 2? Yeah.
What?
So you get 0.2.
I just think
What did you get?
0.286.
Yeah.
we show parents are.
What did you guys get?
0.286.
Excellent. That's what I got.
Is it m to the negative 2?
Now let's take a look at the units. Good question. We got molar squared here. We got molar to the 4th power down there. So what would it be? Molar to the negative 2nd. Exactly. Very good. See, these units are going to be. Are they? Hey, does that mean Kc is always molar to the negative 2nd? No, it totally depends on what the equation is.
Wait,
This equation will change. What's that?
There's 2 on the
Because I
top.
got
4 on the
molar squared here, molar to the 4th down there.
Yeah.
Okay. All right. Everybody go with that. So there were 2 things, actually 3 things I wanted to point out to you here. 1, divide by the size of the container. Okay. 2, watch your order of operations in math. And thirdly, the units. They will not always be what you think they are. Okay. Now let's do one. That again is still pretty easy. Let's do one that you're going to see in the lab tomorrow. Okay. This is about. This is the ones I want to talk to you about. They're much harder. If I didn't explain it, I don't think you would get it. So copy this example down, and then we'll do this. This is very similar. I purposely chose this one. It's pretty much what you're going to be doing in the lab tomorrow. Obviously, you won't be adding A to B. You'll be adding real chemicals tomorrow. Yeah.
Wait, the last one that we did, when we divided by liters, doesn't it make them all moles per liter or no?
Molar.
You divide moles by liters, which gives you moles per liter, which is molar, capital M, molar.
Okay, that makes sense.
The capital M does not mean moles. It means moles per liter.
Or pre-Xan.
All right.
This is fun.
Yeah.
Love it.
Now, this one is a problem. I'm not given all of the equilibrium concentrations. You can't just go start plugging those guys in and dividing them out, raising their coefficients. It ain't going to work. Because here's the problem. It tells me I place 1.4 moles of A and 1.4 moles of B in a 2-liter container. Well, that's nice, but that's not what there is in equilibrium. I can't use those numbers. It tells me after equilibrium is established, 0.3 moles of C is present. That's good. I could use that number, but that's the only one I could use. How the heck am I supposed to do this? Let me show you. I have to do something, what we call in chemistry a lot of times, ice. Ice, ice, baby.
So we have to sing.
All right, so you got to sing while you're doing this.
Gotcha.
ICE it stands for initial, change, and equilibrium. All right, let's look at my initial concentrations here. Okay. Initial concentrations of A, B, C, and D. How much A do I have? Well, I don't have 1.4 moles. I have to divide that, like I just showed you, by the size of the container, but I made it nice and easy. What will the answer be? 1.4 divided by 2 is what? 0.700 molar,
Sure.
right? Okay. So I've got 0.700 molar of A, and I've got 0.700 molar of B. Initially, how much C and D do I have? How much C and D do I have? No. I have 0. It hasn't reacted yet. I just threw them into the container before they actually react. I have no C and I have no D. Now, here comes the here comes the key to this. I don't know what the equilibrium concentrations are right now, but I do know how they're related to the equation. I know how they're going to change. Okay? What's going to happen to A and B? Are they going to go? Is that 0.7 going to go up or down over time? It's going to go down, and it's going to go down. It's going to decrease by some factor. We'll call it x, minus x and minus x. Now, what's going to happen to the concentration of C and D? It's going to go up, but C is going to go up by what factor? Yeah, he's going to go up by a factor of 2x, and D is going to go up by a factor of x. You see it?
Yeah.
So, this is so cool. I can tell the equilibrium concentrations in terms of x. I know at equilibrium, this is where the E comes, ICE, equilibrium concentrations. Equilibrium. ICE. From now on, I'm not going to write out initial change in equilibrium. I'm just going to write ICE. All right? At equilibrium, I'm going to have 0.700 minus x. I'm going to leave out the molar just because I don't have much room here. 0.700 minus x. What's my equilibrium concentration going to be for C? 2x. And my equilibrium concentration for D will be 0 plus x, which is x. There it is.
Wow, I don't.
Is that fun or what? Say, well, that's nice, but that doesn't help me. Yes, it does. Because I'm given one more piece of information, and that is this right here. At equilibrium, I'm told I have 0.300 moles of C. So I know C, 2x, equals, by the way, not 0.3. Why not 0.3? Size of the container is 2, so 0.15. 0.150 molar. I know that from that. Once I know that, can I solve for x? Sure. What is x going to equal? 0.0750, right? 0.0750 for significant figures. Is that correct, by the way? Yeah, 75? Okay. 75? Yeah. 7.5. Okay, molar. I now know that's x. So do I know everybody else? Yeah. I know he's also 0.0750 molar. I know this guy's 0.700 minus 0.0750. And this guy's 0.700 minus 0.0750. Do the math for that. What do you get for this guy? 0.625 molar. 0.625 molar. And you already have this guy right here and that guy right there.
How'd you get the point?
Oh, by the way, this guy right here is actually this one, 0.150. What's that?
How'd you get the 0.0750? You took.
I know from here I have 0.30 moles of C at equilibrium, which means 2x, the equilibrium concentration, is 0.150. I have to divide it by the size of the container 2. So that means if 2x is 0.15, x is 0.075. So do be careful. I almost made a mistake right here. If you notice this, well, everybody look at me. You're all looking down and doing your calculations. I almost did the same thing. It's very easy to do that. The concentration of C is not 0.075. What is it? It's 0.15. I accidentally circled that. It's 0.150 molar. This guy is 0.075. That guy's 0.625. That guy's 0.6. Now I'm ready to do my Kc. Kc equals. No. C squared D over A times B. So we plug them in. This is so fun.
I thought he was going to say this is so fair.
So it's going to be, what's the concentration of C again? 0.150 molar what? Squared times, what's the concentration of D? 0.0750 molar to the first, divided by, what's the concentration of A? 0.625 molar, and B is 0.625 molar as well. Do your calculations for that, and see what you get for your Kc. Did you do it, Liz? What'd you get?
0.00432.
Anybody else get that? And what are my units going to be?
Molar.
Just molar, right. Now let's see if that makes sense. Does it make sense that I would have a very small Kc, given the fact that I put into the container, look up here, I put into the container 0.70 moles, and at equilibrium, I still had 0.625. Yeah, it makes sense that I only made a very small amount of product if my Kc is a very small number. Isn't that cool? We're going to do that tomorrow.